Welcome to the 2017 AP Statistics FRQ exam. In this video, we're going to focus on question number 2, fully explain the answers. Really great question involving a confidence interval for a proportion. If you know how to find confidence intervals, it's actually quite a simple question. And I actually really enjoy what the problem is actually about. So let's just dive right into it. So the manager of a local fast food restaurant is concerned about customers who ask for a water cup when placing an order, but fill the cup with a soft drink from the beverage fountain instead of filling the cup with water. What? Hold on a minute. I hope nobody watching this video has ever done that before. That is just a terrible thing to do. Why would you ever do that? That's just stealing, for crying out loud. Well, I'm sure some of you have. So the manager selects a random sample of 80 customers who asked for a water cup when placing an order and found that 23 of those customers filled the cup with a soft drink from the beverage fountain. So we're clearly dealing with a proportion here because we have 80 customers and 23 of those 80, so that's going to be a proportion, did the unspeakable, ordered a water cup, but filled it with something such as a soft drink from the beverage machine. Now, this is, of course, a sample proportion. So what is 23 divided by 80? Well, you can grab any calculator and do that real quick. That is a proportion of 0.2875. Okay, so far, so simple, not a big deal here. Let's actually dive into what the question asks us. So part A says to construct and interpret a 95% confidence interval for the proportion of all customers who have asked for a water cup when placing an order, but will fill it with a soft drink from the beverage fountain. Now, understand that's exactly what a confidence interval is for. Our sample simply showed about 28.75% of people did this unspeakable act. But again, that was just a sample. The owner of this manager of this local fast food restaurants wants to know what is the true proportion based on this sample. And that's exactly what statistical inference is, using a sample to make a judgment upon a population. So we got to do a 95% confidence interval. All right. I go with what I call the 4 steps to a confidence interval. Other people might teach this as 2 or 3 steps, but I like to go with 4 steps. So we have to name the interval in context to address exactly what it is we're looking for. Check the conditions that allow for this interval to be possible. Do the work to actually produce the interval. And then, of course, interpret the interval in context. So here is all of my work for those 4 steps. I'll go through them slowly one at a time. So step 1 here in the top left-hand corner, the name. This is called a 1 sample Z interval for the proportion of all customers who ask for a water cup, but fill it with, sorry for the typo there, but fill it with a soft drink from the beverage fountain. Now keep in mind we're doing the proportion of all customers, right? We only know our sample, which was from 80 customers, but we're trying to use that sample to estimate what's true for all customers, the proportion for all customers. You can even use the phrase population proportion. Now this is a Z interval. The reason why it's a Z interval is because we are going to base this entire decision on a sampling distribution, and that sampling distribution is following a normal distribution as long as our conditions are met, which is why we do have to check those conditions. So, first condition that I hope you were taught is that the sample must be random to avoid bias. The second condition is that the sample of 80 is assumed to be less than 10% of all customers to allow for independence. The sample did include 23 successes, people who filled it with a soft drink. Again, I'm not calling them a success. That's actually the wrong thing to do, but that is what we're looking for, so they get labeled as a success. And the remaining 57 out of 80 people were considered failures, even though they did the right thing and filled their water cup up with water, but those are considered failures because that's not what I'm looking for in this problem. Now, since both of those successes and failures are larger or equal to 10, a normal model can be used for that sampling distribution, which is why I'm going to be using a 1 sample Z interval. All right, now comes step 3. Again, my personal favorite because it's the math part, right? So this is where we're going to say, all right, let's start with our sample proportion, 0.2875. We're going to go up and we're going to go down by what is known as the margin of error. Now, the margin of error is a combination of 2 things. First, our Z star, that's 1.96. Let me quickly walk you through how I got that. So if we're 95% confident, we want to figure out what Z-scores represent the beginning and end of that interval. Now, the good news is the beginning and the end are going to be the same thing, just negative on the left, positive on the right, because again, it's a confidence interval for the center, middle, 95%. So here we're going to actually go to invert norm to get this value. So invert norm is going to get this for us. And it asks for the area. Now, we could either have it be the area to the left, to the right, or in the center. Now, if you have this command, you could select 0.95 for the area in the center, but you would then need to change it to center. And that is going to get you the z-scores that have 95% in the centers. That's a z-score of negative 1.96 to positive 1.96. Now, the negative and the positive is accounted for in the fact that I'm adding and subtracting, plus and minus my margin of error, but that is how I got that. Now, if you have an older edition of the calculator, when you go to invert norm, you don't have the option for left, center, and right. That means your calculator is automatically set to left. So this is where you got to do a little bit of thinking. If I'm 95% confident in the middle, that means 5% is left out. But that 5% gets split up due to symmetry, 2.5 at the bottom, 2.5 at the top. So if your calculator doesn't even give you the option for going left, center, or right, that means that you are automatically stuck in left. So here, the area it's looking for is the area to the left of the interval, which is 0.025. That'd be that 2.5% at the bottom. So now when you go and hit paste, you will get the negative 1.96, but you need to understand that that means the other side is positive 1.96 because of symmetry, it's perfectly balanced. And again, that's where I got the z star of 1.96 from. Hopefully that is pretty common sense. Next up comes the standard error. This is the same formula as the standard deviation for a sampling distribution, but because I don't know the true p, all I know is my p hat, I have to use my p hat instead of p, which makes it called standard error. It's like the twin brother standard deviation. So I'm taking my sample proportion, 0.2875, times the opposite of it, 1 minus 0.2875. Obviously, you could do that math, maybe even in your head if you wanted to, divided by the square root of your sample size. Put all of that together, take the 1.96 times the standard error, which I got to be 0.0506, multiply those together, and together you get the margin of error. So that's the plus or minus 9.92%. So my sample was 28.75% of people that did this unspeakable act of filling their water cup with something other than water. I'm going to add, I'm going to subtract to get the ends of my interval. So very, very simple. Adding and subtracting, I got an interval of 0.1883 to 0.3867. Now comes the fourth step, which is, I'm not going to say the most important step, but one that a lot of kids tend to forget about sometimes. That's actually interpreting it in context. So I'm 95% confident that the true proportion of all customers at this store that would ask for a water cup but filled with a soft drink from the beverage fountain, oh my gosh, is somewhere between 18.8% and 38.7%. So the 28.75% was simply what my sample showed, but because it's exactly a sample and samples do vary, the truth could be a little bit more, the truth could be a little bit less, and that's how I come up with my interval. But again, you're emphasizing in your interpretation here 95%, and what it is you're looking for, again, the true proportion of all customers that would do this unspeakable thing, and then your left and your right side of the interval. So pretty nice, pretty simple, pretty easy there, I think, if you know how to do a confidence interval. All right, so next up is part B here. Part B says the manager estimates that each customer who asks for a water cup but fills it with a soft drink actually costs the restaurant 25 cents because you're basically stealing. You're getting some free soda or pop or whatever you call it, wherever you live. I call it pop around here. But anyway, you're getting something for free when, remember, you asked for a water cup and didn't pay for it. So that per person costs about 25 cents. So suppose that in the month of June, there were 3,000 customers in total that asked for a water cup when placing an order. So maybe they keep track and every time they note how many water cups they give out. 3,000 total customers asked for a water cup. Using our confidence interval, give an interval for the cost that this could potentially hurt the restaurant. You know, what is this? With the fact that people do this, what's it actually going to cost the restaurant? So first, I'm going to start off with my interval. Remember, my interval was for the proportion of people that would do this unspeakable act of filling a water cup with something other than water. So then I said, okay, well, wait a minute. Now I'm going to multiply that by 3,000 because that's a proportion of people. If I have 3,000 people, then 18% of the 3,000 people would be 564.9 people. 38.67% of that 3,000 would be 1,160.1 people. So this interval here is not for the proportion, but this interval is for the number of people in the month of June that could potentially do this unspeakable thing. So again, as much as I don't know what the exact proportion is, I don't know what the exact number of people is, but if I multiply both ends by 3,000, I can get an interval for the people. Next, what I'm going to do is convert that to money. For every one person, it's a cost of 25 cents. So I'm going to multiply all of those. I'm going to multiply all of these people by 20. Oh boy, I'm getting really messy here. I'm going to multiply my amount of people by 25 cents because each of those people that do this are going to cost me 25 cents. So taking the 564.9 people, 25 cents per person is what this is going to cost me, means that it could cost me as low as $141.23. Or if I take the high end, the 1,160 people, multiply that by the 25 cents, I get $290.03. So all in all, how much is this going to actually cost the restaurant? Because they're essentially being stolen from, right? They're being robbed. Well, I'm 95% confident that the cost due to people using water cups for something else is somewhere between $141.23 to as high as $290.03. So again, that's all based on my original confidence interval, which was a proportion. I converted it to the amount of people out of 3,000, 25 cents for each person that does this, and that's how I was led to these final values for what the cost could be. All right, all in all, I don't think it's a very difficult problem. Confidence intervals are not very complicated. The key thing is making sure you follow through on the 4 steps, addressing all of the conditions and all of the proper vocabulary and context to making it really the best answer you could give. All right, see you in the next video. Hope you enjoyed this one.